Hello friends, welcome back to my channel. Today in this video I'll be discussing a numerical that is based on diffusion in solids. So I'm calling this as numerical number 2 because I have already discussed one numerical in my previous video. Those who have not yet seen that video, you please visit my YouTube channel and watch that video. Please subscribe to my YouTube channel and tell your friends to subscribe to my YouTube channel, and don't forget to hit the bell icon because that will help you in knowing about any new video that I post on my YouTube channel. So let us begin today's discussion. So this is numerical number 2 that is based on diffusion in solids. So first let us look at the problem statement. Problem statement for this numerical is, you can see, hydrogen is flowing through a pipe made of unvulcanized neoprene rubber at 2 standard atmosphere and 25 degrees Celsius. The inner and outer diameters for the pipe are 25 mm and 50 mm respectively. The solubility of hydrogen in the neoprene rubber is 0.053 centimeter cube measured at STP per centimeter cube of the rubber per atmosphere. The diffusivity of hydrogen through the neoprene rubber is 1.8 into 10 to the power minus 6 centimeter square per second. Calculate the rate of loss of hydrogen through the wall of the pipe by diffusion per meter length of the pipe. Okay, so let us understand the statement. So you have a pipe that is made up of unvulcanized rubber. You have a pipe that is made up of unvulcanized neoprene rubber, and total pressure is given to us. So total pressure is 2 standard atmosphere. Hydrogen is flowing through that pipe at 2 standard atmosphere, and temperature is also given. Temperature is 25 degrees Celsius. Then inner and outer diameters for the pipe are given. The inner diameter is 25 mm, outer diameter is 50 mm respectively. The solubility of hydrogen in neoprene rubber is given. It is 0.053 centimeter cube STP, centimeter cube measured at STP per centimeter cube per atmosphere. The diffusivity of hydrogen through the neoprene rubber is given to us. It is 1.8 into 10 to the power minus 6 centimeter square per second. So based on this information, we are supposed to calculate the rate of loss of hydrogen through the wall of the pipe by diffusion per meter length of the pipe. So for the diffusion that is occurring through the wall of the pipe, we are supposed to find out rate of this diffusion. The rate of this diffusion per unit length of the pipe. That means in this case, the length of the pipe is indirectly given to us. Okay, so let us first collect all the given information and then we will solve that. So first let us collect the given information. Let us see what is given to us. So first information is, we will collect it like this: hydrogen, and I'm going to denote that by A. So hydrogen is flowing through a pipe. The pipe is made up of unvulcanized rubber, unvulcanized neoprene rubber. The pipe is made up of that material. Then okay, I have noted over here. So the pipe is made up of unvulcanized neoprene rubber. Now let me erase what I have written, because you have that statement over here. The pipe is made up of unvulcanized neoprene rubber. Then as A is flowing through the pipe, it gets lost through the wall. So as the gas, that is as hydrogen gas is flowing through the pipe, it is getting lost through the wall of that rubber pipe. Pipe inner diameter is given, and we are going to denote that by di. So di is given as 25 mm, and I have converted it to meter by multiplying with 10 to the power minus 3. So it is 25 into 10 to the power minus 3 meter. Then outer diameter is also given. Outer diameter is 50 mm. So again I have converted it to meter. So it will be 50 into 10 to the power minus 3 meter. Solubility of A, that is solubility of hydrogen in the rubber, is given. It is 0.053 centimeter cube at STP per centimeter cube of rubber per atmosphere. That is, you can also express it in meter cube. So it will be 0.053 meter cube at STP per meter cube per atmosphere. So when you have meter cube in the denominator and meter cube in the numerator, so the value will not change. So you just have solubility is equal to 0.053 meter cube measured at STP per meter cube per atmosphere. Then diffusivity of A is given, that is diffusion coefficient of A in the rubber is given to us. It is 1.8 into 10 to the power minus 6, but it is given in centimeter square per second. So if you have to be consistent while using the units, we'll have to change it to SI system, that is we'll have to change it to meter square per second. So it will be 1.8 into 10 to the power minus 6, and in order to convert centimeter square to meter square, we'll have to multiply it with 10 to the power minus 4. That's why you'll have it as 1.8 into 10 to the power minus 6 into 10 to the power minus 4, which makes it 1.8 into 10 to the power minus 10, and now it is meter square per second. Okay. Then temperature is given to us. Temperature is 25 degrees Celsius, and we are going to convert it to Kelvin. So how to convert that? Just add 273.15. So 25 plus 273.15 is 298.15 Kelvin. Pressure is given. Pressure is 2 atmosphere. You can convert it to Newton per meter squares. For that, we'll have to multiply it with 1.013 into 10 to the power 5 Newton per meter square, because 1 atmosphere has 1.013 into 10 to the power 5 Newton per meter square in it. That is, 1 atmosphere is equal to 1.013 into 10 to the power 5 Newton per meter square. So over here it will be 2 into 1.013 into 10 to the power 5 Newton per meter square, which gives us this value, that is P, that is total pressure is 202,600 Newton per meter square. Okay. So in this step we have converted here itself atmosphere to Newton per meter square. So this is given. Again, you have the rubber pipe. I have tried to show it with the help of a schematic diagram. So you have a pipe like this, pipe made up of neoprene rubber, and then hydrogen is flowing through it. This pipe is made up of neoprene rubber. So this is neoprene rubber tube, and through this hydrogen gas is flowing. And as hydrogen gas flows, it is getting lost. So it will be getting lost through the wall of this cylinder. So it will be lost to the atmosphere. Okay. So we will represent it in a different diagram. So you have on this side, you have the, you can say, front view of the pipe. So you have the inner diameter, you have the outer diameter, and this is, you can say, the side view of the pipe. So you have some length, and so you have the inner diameter. Inner diameter is given to us as 25 mm. Outer diameter is given to us as 50 mm. Then length for which we are going to do calculations is 1 meter. We are supposed to find out rate per unit length of the pipe. So in our calculation, length will be 1 meter, inner diameter is 25 mm, outer diameter is 50 mm. So what the geometry of the pipe we have depicted in this diagram. And on the inner surface of the tube, we are considering a point or a point, and I'm naming that point as point 1, and on the outer surface we will be considering a point that is represented as 2. Okay, so inner surface of the tube is having a point. We are considering that point as point 1, and on the outer surface you have point 2. Okay, so hydrogen will be diffusing as hydrogen is flowing through the tube like this. As it moves through the tube like this, it will be getting dissolved in the rubber, and then it will diffuse through the rubber, and then it will come out in the atmosphere, and it will be lost in the atmosphere. So what is the rate at which this loss occurs, or what is the rate at which hydrogen diffuses before coming to the outer surface? We are supposed to find out that in this particular numerical. So rate of loss of hydrogen per unit length is to be found out. Okay, so I hope the problem statement is clear to you, and what are we supposed to find out, that is also clear to you. If you have any doubt regarding whatever I discuss in my videos, you please mention that in the comment section. I will definitely reply to your comments. Okay, so having noted what is given and then what are we supposed to find out, let us go for the solution. Let us go for the solution of this. So as you know, hydrogen is flowing through a rubber pipe. That means this is a case of diffusion through a cylinder wall. And what is the equation for getting rate in this case? I have already discussed in my earlier video, which is available on my YouTube channel. You please visit that and watch the video. So this is a case of diffusion through a cylinder wall. The formula to be used is RA is equal to dA into AC divided by R0 RO minus RI into CA1 minus CA2, where RA is the rate, dA is the diffusivity, AC is the area through which mass transfer is going to take place, R0 is, or RO is outer radius, RI is inner radius, CA1 is concentration at point 1, which I just talked about, and then Ca2 is concentration of A, that is hydrogen at point 2. So I will show you the schematic. So Ca1 is concentration at this point and Ca2 is concentration at this point. R0 is RO is outer radius, Ri is inner radius. dA is diffusivity of A, which is given to us. AC is the area through which diffusion is taking place. We need to calculate that this area in this first before you go and use this equation. So dA is given, RO and Ri are to be calculated from the given information. They are not directly given to us. Instead of radius, what they have given is the diameters, and we need to find out radius from that. Very easy job. AC is to be calculated, that is area available for, or area through which diffusion is taking place. We have to calculate it from the given information. Ca1 and Ca2, they are to be calculated from the given information. And finally, once you get all the terms that are present on right hand side of this equation, you can directly use that equation to get the rate, which we are supposed to finally report in this particular numerical. Okay, so let us now get the quantities that are required First we need to get Ri and Ro. Ri, simply it is half of the diameter. Inner radius is half of the inner diameter. So diameter is 25 into 10 to the power minus 3 meter, that is given to us. So if you put that value, so it will be 0.0125 meter. So inner radius for the tube is 0.0125 meter. Similarly, you have to get outer radius. So outer radius is Ro is equal to outer diameter do by 2. So it will be do is equal to 50 into 10 to the power minus 3 meter. This is given to us. So if you use that, you get Ro as 50 into 10 to the power minus 3 divided by 2, which is 0.025 meter. So this step is over. So we have got the value of Ri, and then we have also got the value of Ro. Now let us move to the second step, where we are supposed to calculate the area through which diffusion is taking place. That is, we are supposed to calculate AC. And we know, I have already discussed about this formula. For diffusion through the wall of a cylinder, the area through which diffusion occurs is given as AC is equal to 2 pi r Lm into L. You please refer my earlier video or watch my earlier video to understand this. In this case, L is 1 meter, since we are supposed to find out rate per unit length. So that's why length is 1 meter. RLM we have to calculate, and we are going to calculate that from Ri and Ro, which are now known to us. What is the formula? So here the step for calculating RLM, now we can see the formula is Ro minus Ri divided by ln of Ro by Ri, which is RLM is nothing but logarithmic average of Ro and Ri. So if you just put the values, Ro is 0.025 minus Ri is 0.0125, so it is 0.025 minus 0.0125 divided by ln of 0.025 divided by 0.0125, which is nothing but 0.018 meter. So RLM is 0.018 meter. Now once RLM is known to us, we can use this formula to get the area, that is AC. So finally, calculation of AC, you have AC is equal to 2 into pi into 0.018 into 1. So all the values are used in the equation, and you get AC as 0.1131 meters square. So area through which diffusion is going to take place is 0.1131 meter square. Then next, so we have covered two steps. In first step we have got Ro and Ri, and in the second step we have got AC. Now let us move on to the third step, which is calculation of Ca1 and Ca2. Again, the steps involved in these calculations are similar to the steps we followed in numerical number 1. You please check my previous video. So again, let us have a small schematic. So you have the rubber tube. This is 0.1, this is 0.2. So Ca1 is molar concentration at 0.1. So Ca1 is concentration over here. Ca1 depends on the amount of A that dissolves in the tube wall at 1. So we are talking about concentration of A in the rubber at this point, and that concentration, it depends on how much A dissolves in the tube wall at 1. How much A dissolves in the tube wall at 1, that will decide its concentration at 0.1, which is nothing but Ca1. Okay, the amount of A that dissolves, again the amount of A that dissolves depends on its solubility, which is given to us. The solubility is, it is given 0.053 meter cube measured at HTP per meter cube per atmosphere. So now our task is we have to convert meter cube at HTP to kilomole at given temperature and pressure. So the important step in getting Ca1 is we need to convert meter cube to kilomole. We want to convert meter cube at HTP to kilomole at given temperature and pressure. And we know at HTP pressure is 1 atmosphere and temperature is 0 degrees Celsius. That is 0 plus 273.15, which is 273.15 Kelvin. Okay. So again, continuing with this, we will apply ideal gas law at HTP. And to begin with, we are using this information. Everyone knows that at STP 1 gram mole of an ideal gas occupies a volume of 22.4 liters. For every ideal gas, 1 mole of that gas will be occupying a volume of 22.4 liters at standard temperature pressure conditions. Or we can state it like this: 10 to the power minus 3 kilomole. That is, instead of writing 1 gram mole, I am writing 10 to the power minus 3 kilomole of an ideal gas occupies a volume of 22.4 into 10 to the power minus 3 meter cube. That means instead of writing the volume in liters, I have written it in meter cube by multiplying with 10 to the power minus 3. So ideal gas law is PV is equal to nRT. So I'll put all the values. Pressure is 1.013 into 10 to the power 5 STP condition. Volume is 22.4 into 10 to the power minus 3. That is equal to N. Moles is 10 to the power minus 3 kilomole. R is 8314. Again, be careful while using value of R. So if you are using R is equal to 8314, then pressure has to be Newton per meter square and the amount of substance should be in kilomole. So here pressure we are using in Newton per meter square and the amount of substance we are using in kilomole. That's why I have taken this value 8314 into temperature, that is 273.15, 0 degrees Celsius. And for time being, I am calling this relation as 1. Then we will apply ideal gas law at given conditions. What are the given conditions? Temperature is given and pressure is given to us. So again, ideal gas law is PV is equal to nRT. So pressure is 202,600 Newton per meter square, 2 atmosphere, which is 202,600 Newton per meter square. We have done that previously. Then volume is 0.053 volume. We want to know kilomole of gas that will be occupying this much volume at given temperature and pressure. That is equal to X. That means right now I don't know how many kilomoles occupy this volume. So I'm calling that as X. So it is X into 8314 into 298.15 and I'm calling this as equation number 2. Okay. So you have relation 1, which is obtained when we apply ideal gas law at STP, and equation 2, which is obtained by applying ideal gas law under given conditions. Okay. So let us move ahead. Now again, continuing with the same step, we are calculating Ca1 and Ca2. So from the previous slide, let us collect the two equations. So first equation was this thing and the second equation is this. This is second equation. Now we will take ratio of equation 1 and 2. So if you take the ratio, that is numerator upon numerator is equal to, now LHS upon LHS is equal to RHS upon RHS. So you have 1.013 into 10 to the power 5 into 22.4 into 10 to the power minus 3, the LHS of equation 1, divided by 202,600 into 0.053 LHS of the second equation, that is equal to 10 to the power minus 3 into 8314 into 273.15 RHS of equation 1 divided by x into 8314 into 298.15 RHS of equation 2. Okay, now our task is to get x. Simple task. So if you simplify, you'll get this. So all this will be 0.2113, that is equal to, and all this will be 9.16 into 10 to the power minus 4 divided by x. And again, if you solve it, so it will be 9.41 into, you please read it as 9.16. Just a minute, let me, this is 9.16 into 10 to the power minus 4 divided by 0.2113. So that comes out to be 4.45 into 10 to the power minus 3 kilomole. So now we have got kilomole. This many kilomole of gas will be occupying a volume of 0.053 at STP. So that is, so we have converted SA, which was in 0.043 meter cube at HTP per meter cube per atmosphere. We have converted it to 4.45 into 10 to the power minus 3 kilomole per meter cube. And this is nothing but, that means, what does SA tell now? SA tells that 4.45 into 10 to the power minus 3 kilomole of hydrogen is going to dissolve in the rubber at the given conditions. It is going to dissolve per meter cube of the rubber at the given conditions. So this is nothing but Ca1. That means Ca1 is 4.45 into 10 to the power minus 3 kilomole per meter cube. And let us talk about point 2. So as hydrogen diffuses through this rubber wall, and as soon as it comes on the surface, it will be getting lost. So that means at any point of time there will be no hydrogen on the outer surface, or to be more specific, there will be no hydrogen at point 2 at any given instant. That is, what is the reason for that? As soon as hydrogen comes at point 2, it is removed by air, and therefore at any instant there is no hydrogen at point 2, and that's why Ca2 is 0. Okay, so at this point we have got value of Ca2. We know that Ca2 is 0. Earlier we got value of Ca1, and that's the objective of this step. The objective was to get Ca1 and Ca2. We have achieved that objective. We have got the values. Now let us move on. Finally, we are left with calculating Ra. So Ra, the equation is, again, once again I am writing, Ra is equal to dA into AC divided by Ro minus Ri into Ca1 minus Ca2. Now let us collect what are the values. dA is given, it is 1.8 into 10 to the power minus 10 meters square per second. Then AC we calculated previously, it is 0.1131 meters square. Then you have R0, which we have again RO rather, we have got it earlier, it is 0.025 meter. Ri we got it earlier, 0.125 meter. Ca1 we got previously, it is 4.45 into 10 to the power minus 3 kilomole per meter cube. Then Ca2 is again we got 0. We know why it is 0 now. Therefore, if you put all the values, Ra will be 1.8 into 10 to the power minus 10 into 0.1131 into 4.45 into 10 to the power minus 3 minus 0 divided by 0.025 minus 0.0125. And if you simplify, you will get Ra as 7.25 into 10 to the power minus 12 kilomole per meter square per second per meter length of the pipe. That means hydrogen is getting lost at this rate, 7.25 into 10 to the power minus 12 kilomole. Now there will be no area in the unit. We have considered area over here. So the unit for this rate will be simply kilomole per second and per meter length of the pipe. Okay, so that means the rate of loss of hydrogen is 7.25 into 10 to the power minus 12 kilomole per second per meter length of the pipe. Length is 1 since we need to find out rate per unit length of the pipe. So this is how you have to solve numericals like this. I hope this video will be useful to you. If you have any doubts, you can mention that in the comment section. Please subscribe to my channel. Ask your friends to subscribe to my channel. Hit the bell icon. That's because you'll be getting notified as soon as I upload any new video. For time being, thank you for being with me. Have a nice day. Bye bye.